Good afternoon. My name is Jim Fawcett. This is the 5th video in a short sequence of videos about the Rust programming language. So far, we've introduced the Rust language, generated, hello world, and set up an environment to develop Rust code and so on. We've talked about the ownership model. We've talked about an object model, the object model that Rust uses, and we've talked about Rust generics. In this video, we're going to discuss code structure. Okay, so code structure, we write code in files, of course, and the issue is that in lots of projects, the file system, the files that we use get pretty big. We have lots and lots and lots of files. Not uncommon for a project to have several 100,000 lines of code, maybe 1 million lines of code, maybe more. The Linux kernel has 15 or 20 million lines of code. The Windows operating system has 60 or 70 million lines of code. Not at all uncommon for projects to get very, very large. So in order to manage that kind of complexity, we need to divide and conquer. We need to break it down into pieces that a mortal human being can understand. And so we divide our programs into packages. And in Rust, a package consists of a directory that's built with the Cargo tool, has a source directory that may hold what the Rust community calls binaries. It means an executable that with a main, that's the entry point for the program. Might be libraries, which are compiled separately and loaded to build a binary. A file might be a module that's loaded by the binary file. The binary, we talk about that as being the root of the root file for the crate. It's just the top of the feeding chain. And the question is, how do we pull all that stuff together? And that's what this presentation is about. So a crate is, in binary form, is either a library or an executable. In source form, it's all the the files and modules and libraries that go to build that one specific binary or library. The package, when we build a package with Cargo, it sets up a source directory and creates a file called Cargo.toml. Cargo.toml holds metadata about the file and allows us to cite dependencies for the package. And when we build it, Cargo will create a target directory, and inside the target directory, if we're building a debug build, for example, we'll have a debug folder, and in that there'll be an exe. If we're building a binary, there'll be a rlib, lib package name, .rlib if we're building a library. In Rust, we can tell Cargo that we want to build a static library. We can tell Rust we wanted to build a dynamic link library or shared library if you're working in the Linux world. If we don't specify anything, the current version of the compiler takes its choice, and it looks to me like its normal option is to build a static library. I haven't dug into that a whole lot, so I don't know for sure, but it looks that way. But anyway, we can build by giving Cargo the right command line arguments. We can tell it to build whatever we want it to build. Okay, so a crate, the source form of the crate is composed of, the modules, the root, the crate root, either main.rs or lib.rs, and and 0 or more files that are modules exist in the source directory, and the crate, the root specifies dependence on that with the keyword mod. And, so the crate root loads any modules identified with the keyword mod at the top of its source. And then each module, lower level module, can load other modules in the same way, declaring a mod file name at the top. And the crate can also specify dependencies, and this is where things get interesting. They can specify dependencies on local libraries, on external libraries, on remote libraries. So we'll get into that a little bit. I'll tell you a little bit more in the succeeding slide, but Cargo, the build manager, the package manager and build manager and execution manager, does all those things and does them all well. Let's just specify all that. So anyway, we wind up when we're done building with a package name.exe or live package name.live, or package name is whatever we told Cargo to, when we say Cargo new is some name, that's the package name. If we say Cargo new and don't specify the package name, then the directory that we're in becomes the package name. So here's a view of the Cargo.toml file. And so we have a package section that just lists the metadata for the file, the name, version number, author, edition. This is the latest edition of Rust, the Rust C compiler. And here's, in this dependency section, here's where Cargo specifies, where you specify to Cargo the dependencies that you need. So you just go in to the Cargo.toml and you edit in mylib equals path, :/mylib. So this means that in some sister directory to this package, I wanna load a library that I created there. And this line says, go to crates.io and load a crate called Certi. It's a serialization deserialization, very popular crate. And I just picked it because it was, near the top of the list, and just something to specify for no good reason for this demo. And you need to specify the version number that you want to use. And there's attributes you can say anything later than this or whatever. So the Cargo build process then will load mylib and Certi crates before building this crate. And it's really, really convenient, really easy to use. So package is a collection of these directories and files that are the basis for builds. So every time I say Cargo new, I'm building a package. And that creates the Cargo.toml file, creates a source file. It doesn't create these two. It creates target when you build it. And you can create an examples directory and load binaries there that let's say I'm building a library and I want to exercise it, or I want to demonstrate it to my users. I can build an examples directory and put in demonstration binaries that load my library and exercise it in different ways just to show people what it does. Or I can use it for a regression test. The Rust build system works transitively, so each Cargo file can have multiple dependencies, and so as I branch out, each dependency, so for example, this dependency to mylib just goes to another directory where there is a Cargo file, okay? It doesn't go down into the target directory where the library is. It goes to the directory where the Cargo file is for that library. And so, the build process reads that, and if that has dependencies, it branches out and reads those. And so it's just walking this tree of dependencies in a transitive way to compile complete our build. So build start with a package root Cargo.toml, parse the defined dependencies, load the depending library and parse this Cargo.toml, you know, on and on and on, and then build the local crate along with its dependencies. So I now want to talk a little bit. There's some interesting things that the Rust build system does. We can build a library crate. The way we do it, we say cargo new, and we specify lib. If we don't specify this lib argument, then it'll build a binary. And we can optionally specify the name. Otherwise, it'll just use the name of the directory that we're in. And so that builds a lib.rs containing a single configured test, a little trivial little test. And I can start adding code to it. And this little test shows me how to build individual tests. So I add a little bit of code to my library. I write a test to check it out. I add a little more code to my library. I write a test to check it out. Really, really nice process. Each test passes if and only if there are no failed assertions. As long as it doesn't assert, then the test passed by definition. So that tells you how you got to write your, your tests are going to be a series of assert statements. And as long as they all don't assert, they don't say this is, as long as the predicate is true, then the test passed. So each time we add a few lines of code, we add a small test. And we just say cargo test, and that builds, a little internally defined main that just exercises all those tests one after the other, a little executor that exercises all those tests one after the other. And it makes for a really nice building process, really works well. Okay. Code test process allows us to very quickly find errors. If a test fails, we know where to look, okay? We just added a little bit of code and we ran a test. We added some more test code and we ran the whole series of tests. When we say test, it doesn't just run this one little one we just added, it runs a whole battery and they're quick, bang, 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 bang. And so we can see, and what happens is when a test finally fails, we know it's somewhere, right around that last few lines of code we added. We don't have to search all over the place to find where the problem was. And so it's a really nice way of constructing projects. I want to take a few minutes to just talk about what I think of as a classic code structure. Here we have an executive. We have a couple of components. One component is ordinary kind of helper thing that the executive composes. And another one is a component that builds a implements a trait and defines a factory function. And the factory function will create an instance of this component. So, this, what that does, what that process of building a trait and a factory function is, it isolates this component from, in a build sense, from these other guys. So we'll see a little more of that in a minute. And then there's any number of libraries that we have sitting down here that lots of these packages will call, and we probably won't add. So in this example, every one of these guys calls display. So it's counterproductive to show all those dependencies because it just depends on everybody, and all those lines obscure the basic structure. Okay, so inside those, I have a trait. If the word trait bothers you, go back and look at the previous video, previous two videos. But I have a trait that I'm using like an interface. So a trait for component A, and here's component A. So component A has to implement that trait. And I have an executive that's going to use component A. And what it does is the executive calls the factory function that's defined in a component and gets back a reference to this trait. So it can call any of the trait functions, but it can't do anything else with the component. And it turns out, we'll see in just a minute in the next slide, that the text of that trait and the factory function don't have any implementation detail, and so that means that the design of these guys are strongly isolated from the component. Okay, so here's the trait tcomp a, you know, do work, get message, set message, whatever you happen to need. I have a little demo little demo that implements the structure. You know, if you go to the repositories where I have all this demo code, there's a, you know, Rust models repository that has all this demo code. You'll find an implementation of this, and you know, just has the trait has these functions. So this is the interface. This is the contract that this component is making to the executive in component B. And the way they get access to it is to call this get instance function. And that returns an instance of this component A created on the heap and pointed to with this box. And box is like a smart, you know, standard unique pointer. And so when box goes out of scope, just like standard unique pointer, it releases its resources. It has them removed from the heap. Okay, so all these guys, you know, executive component uses this factory function, and they use this interface so they don't bind to the implementation details of that component. Okay, good thing. You know, for example, if this component were part of our system that was varying a lot, we don't want these guys to be constantly have to change their design because of the way these things built. So as long as this guy satisfies this interface and doesn't change this factory function signature, we're good to go. We don't have to make any changes here. Really nice way of carrying out an implementation. The real issue here is that as systems get bigger, their dependency structure gets more and more complex. And we can get all bound up and tied up with these dependencies to the point where we just can't make any progress. So we use these separators, this interface and object factory separator, to prevent that creeping dependency. This is called the dependency inversion principle, and really good idea. We use it a lot. So now let's turn a little bit to a model for the compilation of all this stuff. So here's Cargo, and it has built this crate, and so you know, it knows how to get to this root crate, Cargo.toml, the Cargo tool knows how to get to Cargo.toml. You know, if we're in a prompt in that directory, we just say Cargo build, then it goes and parses this Cargo.toml file to find its dependencies, and then, you know, those dependencies branch out into a dependency tree, and it just transitively pulls up, you know, the cargo for each of those dependencies and analyzes that to see whether it's at the end of the dependency chain, or do they have to recurse deeper into this? You know, is there more dependency tree to recurse into? Okay, and then when it's all done, you know, it has all that stuff. It builds this crate and stores it. It builds the code in the source directory and stores it in a target directory. Okay, so now when Cargo builds, we compile external libraries. So Cargo.toml lists, as we saw earlier, it lists the dependencies. Could be a local dependency, local library that we built on our machine, or it could be a remote one from crates.io or GitHub, for example. And so it just walks that tree recursively, pulling up all its resources, and then it compiles a local resource. So, you know, when all these external dependencies have been gathered together, and, you know, and the resources, they're compiled if they need to be compiled, then the crate root is built, and any modules that it specifies are loaded as part of that building process. So, so we go out, grab all those external dependencies, build anything that needs to be built, and now we build the crate itself, and by compiling the crate root and loading any dependencies it describes in its mod keyword with its mod keywords. Okay. Now so that was build. So now when the build is done, now we want to execute stuff, and there's 3 interesting ways to do executions with Rust. One is just to say cargo run, and if I built a binary, it runs it. Okay. If it's a library, it won't run it. It can't. It'll give me back an error message that I can't run this guy for you. But if it's a library, I can run cargo test. I just say cargo test, and it just goes and steps down through all the tests. Normally, there's a whole bunch of little tiny tests, and it comes out and says, first test okay, second test. You give it a name, name 1 okay, name 2 okay, name 3 okay, and and then you're done. Finally, so there's 2 ways. The third way is to run examples. So if I've built my library, I've run all the tests, I'm satisfied with it. Now I start I create an example directory, and I start putting in binaries that exercise that library just to demonstrate for potential users how it works, or maybe to run some tests that are hard to run in, in the library configured tests. So, okay, so we have those 3: cargo run, cargo test, and cargo run example, where an example is the name. It would be an example.rs, a binary file in that examples directory. And when we execute, we have, we enter program main, and then as we call functions, one function creates a stack frame, and if that function calls another function, we create another stack frame, and we get this sequence of stack frames. And when we finish, when we go, each of those stack frames represents a scope. And when the thread of execution leaves that scope, that memory becomes invalid. It's returned to the the runtime system to return and reallocate to the memory manager, basically, because this is native code. And so anything that was on that stack frame is now invalid. Their destructors will be called, their drop functions will be called, and where we go, everything seems to work fine. We have a memory model. We have static memory, which is where the code for the program goes. Any static data. Rust discourages you from using it. You can use it, but Rust discourages you from using it. And heap memory, okay? And then we have, standard in, standard, files, standard out, standard error. We have these normal handles to the external environment. So. And this slide just says what I said about static, stack, and heap memory. So why don't we skip on over that and talk about its interaction with the execution environment. That happens 2 main ways. One is to use these. For example, I can open a file handle. So use a stream object like standard in or standard out. I can use a library, a file handle, for example. This standard IO prelude loads a whole bunch of definitions from the standard library so that I don't have to manually load those definitions. The other way to interact with my environment is through the foreign function interface, and this requires that I use unsafe code. For most things, we won't do that. If I'm writing a library that needs to, wants to talk to a C library, then I need to use the foreign function interface and unsafe code. But that's beyond the scope of what we're trying to cover in this set of videos. Okay, so that's the end of what I want to discuss in this video. Eventually, I don't think I'll be adding any more videos for a while. Eventually, we'll add some videos for the libraries. Before too long, I'm going to take up writing threaded code, using the thread facilities, and I'll add videos. As I come to those things, I'll add videos. Just a couple of quick notes here in the epilogue. This just is kind of a summary. I think these models are a good way to think about a language. The ownership model, the object model, and so on. I built, on my website, I built what I call a Rust story. And these videos were extracted from that Rust story. I'll show you a link in just a minute to how you can get to that if you want to. Okay, so and Rust, is built to provide type-safe operation. That means having no undefined behavior, and it does that mainly through using ownership policies, which we talked about in an earlier slide. So here's some resources for you to look at. So this Rust story models.html takes you to a page in my Rust story that focuses particularly on these kinds of models. The Rust story begins with this prologue page. So if you want to see the Rust story, a story on my website is just a series of link pages that all have to do with one particular topic. So for Rust, I have a set of link pages, okay, that are a lot bigger than what we're talking about in these videos, but the same kind of idea. We've got a bunch of basic demos, code, that I wrote to figure out how Rust works and to help you figure out how Rust works. My website, if you go to jimfawcett.github.io, you'll, you point your browser at that, you'll come up with my website. And from there, on the top, you'll see, it's just, you'll see a, there's, let's pull this over. So there's, there's, this is the Rust Basic Demos library, but if you go to the home, here's stories, and there's a C++ story, a Rust story, and so on. So, that just lets you see those things. So, okay. So with that, I'm going to say, see you later until we meet again. So let's